It'll have dark energy and the fate of the universe in major. We'll be also discussing about the Lambda CDM model. I'm not sure if you all have already checked up on that because that was already given in the project that you are supposed to be doing. So, to begin with, does anyone have any doubts about the project that was shared in the previous session? That will be your minor project too. And your presentation dates are 17th and 18th. That is 1 week from today. So, 2 weekends were given to you to check through the topics. One weekend is already done. You have one more weekend to sit on them, and you will be coming up with a presentation of 8 to 10 minutes, utilizing at least three out of four topics we have discussed since our minor project one. So those topics include stellar evolution, galaxies, cosmology, and compact objects. So, out of these four topics, you will be utilizing at least three to inculcate into your presentation that you will be doing in the next week. So, this is the sum up. We'll have this session to discuss the final part of cosmology, which will also be helpful for your project. Also, our upcoming sessions now, whatever leads to your major project, that is the final project of your this program of astrophysics, that will be purely based on observational techniques, where we will be discussing how to analyze light curves, plot light curves, and various telescopic activities that you can do, various projects online that you can avail and you can try on your own, as well as how capturing and observation and all image transmission, image superimposing, all of that will happen using various filters. Right. I'll also be discussing about the various projects that I've done. So as of now, I've planned around 10 classes or 10 sessions on these observational techniques. We have few sessions based on the projects that I've done. So you can take examples from there. You can ask your queries, and we'll be sorting that out, and we'll be looking into more opportunities for you to do things on your own, wherein we have online platforms where you can check up on various projects or simulations where you can try and capture data and analyze it and develop a light plot of your own and analyze the light plot as well and see what all informations you can get out of it. So a few on the spot assignments also would be given to you, and based on all of that, based on the next upcoming 10 sessions, we'll be having our major project as well. So this is the idea that I have as of now. Hope it goes well, and I will share my screen for today's session.
One thing regarding the project, regarding the PPT on 17th, uh, have you shared any instruction or description on the WhatsApp group?
Oh yes, I have shared the PPT as well as the instruction.
Okay.
Um, I have shared in the group called 6 months September batch home space. Are you on the group?
Yes, yes, I am there. I'm just looking at it.
All right. It was shared on Friday right after a
Like the
session at
project
10:05 p.m.
yes, yes, got it, got it.
Got it? So
Yes,
there is a PPT, there's a PDF that I've shared of the last session's PPT. I've shared it as a whole because there were a lot of students who couldn't attend that session. So this you can refer for all the topics as well as the guidelines are within it. I've also shared a Google Doc below that, wherein you will have to update your name and your topic that you're choosing. And yes, I've just shared those two. Please check that out, and please make sure that you update on the doc as well as follow all the guidelines and topics. Yeah. All right. Okay, so I will quickly share my screen. So since this is sort of like a continuation of our previous session, I will just give you a quick sum up of what was happening in the previous session, and then we'll move on to what we are looking today. So, our today's topic is a very short topic. We should be able to cover it up pretty soon. Present. Got it. Can you all confirm if the screen is visible?
Yes, ma'am.
All right, thank you. Okay, so last session, I mean, last to last week's final session, we had started with the part one for cosmology, wherein we dealt with the first question that had no correct or wrong answers, wherein we discussed the universe around 100 billion years from now. Will it be empty or will it be safe? We had a lot of discussions coming up. There were no right or wrong answers. We just threw in our thoughts into it. Then, if you can check these topics, we dealt with the part one. We dealt with the expanding universe and universe's baby picture, wherein we discussed about Hubble's law and a lot of theorems that came with it. And yeah, the expansion was discussed, and we came up with um, the major formula that dealt with the velocity and the Hubble's constant. And we also had a sort of an activity at the end of the session. Yeah, we also discussed about the cosmic scale factor A and how to apply that. And we also had the Olbers paradox. We discussed the Olbers paradox in detail so that you can look more into it if you are interested. We discussed all the derivations. We discussed how the shell varying and whether, at the end of it, the paradox mainly dealt with whether the universe is finite or infinite, right? So, yeah. So we came to the conclusion that it could be finite, wherein we had a lot of controversies, a lot of questions that came out as part of it. And we dealt with the baby pictures, wherein we looked into the cosmic microwave background and the inflation of the universe and how it was captured with different types of structures and different types of telescopic views. Um, yes, we dealt with the inflation theory and how the inflation theory has expanded and how the expansion of universe is viewed in a better way and how you could understand in terms of the expansion and in terms of this image was discussed. Then we dealt with a couple of activities which I believe all of you have completed. Okay. So today we are dealing with the part two, which is divided into two sections. One is the cosmic drivers, and another one is the lambda CDM model. So moving on, um, can someone tell me before we start the cosmology's first part? What were your major takeaways, or what do you remember the most out of it? I believe we had a long session that day. We had around 2 hours of session, 2.5 hours of session. So there should be something that you could take away from that session. So if if three of you can give me what actually stays in your mind or what you could really carry over, that'll be great.
I mean, I don't really remember exactly which session.
Oh, the one I just revised right now, actually.
Okay. Oh, got it.
Were
So
you present for that session?
yeah, I was there. We had a discussion regarding the question you showed right now, and
Mm-hmm.
my take was that it will be. I mean, we won't be able to see anything because objects must be too far from each other
Mhm.
because of the expansion of the space between the two objects. You're asking about this question, right? Due to the expansion of the universe, will we see anything in the sky or what?
Okay.
So I
And what
remember.
was the conclusion we landed in?
So the conclusion was not exactly any particular one because
Mm-hmm.
we kind of have, I guess, three theories regarding the Big Crunch, Big Bang, and don't know the name, but in which the universe remains constant.
Okay. All right.
So if it is Big Bang and it's expanding and it
Mm.
won't come back, I mean, it won't come back to singularity. In that case, and the expansion is basically the space between the objects is increasing,
Okay.
not the boundary is going away because
Exactly.
the space between the objects is increasing, and that is why it seems the boundary is going away.
Mm.
So, and if after like 100 billion years, I guess it was, though, if there are no, I think the rate at which the universe is expanding is much greater than rate at which stars are. Uh, I mean, they are
Common.
getting nurtured, they are getting born.
Mm.
So, at that point of time, there must be stars that will be born, but the
Okay.
stars will be extremely large that we won't be able to see. So that was
You
my
mean the light years are extremely
yeah,
uh, more?
yes. And if it is
Okay.
big crunch, we, I mean, it could have. I mean, the universe could already have been gone, or else it must be contracting. So we will be seeing many stars, a lot of stars, a bright sky, something like that.
Mm-hmm.
And if it is big crunch, and it could be like pulsating also, like big
Okay.
crunch, then expand, again expansion, and something like that.
All right. Okay. Yeah. Thank you, Nimit. And does anyone want to give your thoughts about the Olbers paradox? Like, if you can give me a quick sum up of what you understood or what you remember from the Olbers paradox. Is there anyone trying to speak?
As I have understood from the Orbital paradox, it was like when we look up at the night sky, there should be a star which gives at light. So, there shouldn't be night. Night shouldn't exist because
Well,
as
I believe there's a lot of disturbance at your end. I'm not able to clearly hear you.
wait a minute.
Yeah, sure.
Is my voice clear now, ma'am?
Yes, it's clear.
Okay, ma'am. So about the Orbis paradox, I actually understood only that, uh, as it's stated, uh, we shouldn't we should have a source for light all the time, since as we go far from the density, I mean, wait a minute, I will. Okay. It was if there is that much stars in the universe,
Mm-hmm.
there should be a source of light even at the night, other than the sun. Even at the night, when our sun is not directly incident on that part of the earth, there should be any other that we should provide the light. But why is there not that? Uh,
Okay.
Paradox, right?
Yeah.
So the problem was, first of all, uh, it was uh, the distance between star. But the second thing was uh, solved by inflation theory. Since we are the universe is expanding, so the distance between the stars is also expanding, which leads to the reduction in density as we go far due to which they are less, I mean, uh,
Yes,
like
you're
food
getting
supply.
there. Yeah.
Also, that assumption was based on the previous outdated model,
Hmm.
where we assumed the universe to be static and infinite. But the current model we use, which is lambda CDA model, lambda cold dark matter model, suggests
Hmm.
the inflation theory. So, if our universe is ever expanding, then it and there's so much distance between stars, it's not like surprising that we don't have uh, light source all of the time.
Hmm. So, okay, the Olbers paradox, what you have told is one part of it, wherein we dealt with, for example, 1 minute, I'm just taking the screenshot of the day. Just leave that up. Uh, Okay. So, one part of it that you have told is accurate because, wherein as the shells are moving further, I'm sorry, are you trying to talk?
No, ma'am.
Okay. So, as the shells are moving further, the stars are moving even further. The distance is increasing, but at the same time, if I may show you that slide again, just for you all to recollect. Yeah, yeah. Okay, okay. So here, if you see, we have shells arranged in front of us, but each shell is having, like, each successive shell is having the amount of stars that's almost exponential to the shell preceding it. Right? So in the first shell, if we have X number of stars, the next shell that is even further has around 4X number of stars. Even going further, it could have 9X number of stars. So as it keep moving, the distance is increasing, but the volume, or but the amount of star, or the density population of the star in each shell, is keeping on increasing, which means the distance moving further should technically be decreasing the intensity, or the sort of brightness that reaches our eyes from these stars. But at the same time, we have found that we have fewer number of stars near us, wherein the brightness, let's say, is luminosity 1, right? Now, as we move forward in the subsequent shells, the stars are more in population. So the intensity that reaches our eyes due to the number of stars, despite the distance between us and that successive shells, the luminosity that could reach our eyes could be more or less equal to 1. Here we are neglecting all the factors about the clouding in between, or any sort of things that could, dim our vision, etc. We are also assuming that the light years are reaching us on the same note. Okay, so keeping all these in mind, we said that although the distance is increasing due to the population of stars in each shell, and if the intensity reaching our eyes from a farther shell is equivalent to the intensity that is reaching from a nearer shell, then if the universe is not finite, meaning if the universe is infinite, then we could be having a sky that would never have a night, because all the stars, the intensity would be reaching our eyes, and it could look more or less like a day. So, since that is not happening, Olber's paradox has put in the fact that this could be a proof for a finite universe. All right, so this was Olber's paradox, just to give you a sum up on. Anyway, so I'm going to the next today's session, just quickly starting up with today's session. Today we are looking into cosmic drivers, and the first thing we'll be discussing about is the dark energy and accelerating universe. Right. So we have already discussed about dark matter and the kind of energy associated to it, and how much of the universe is covered by dark matter, or how much of the universe is occupied by dark matter. So for the most part of the 20th century, that is the 1900s part, we assumed, or the astronomers assumed, that while the universe was constantly expanding, well, as you've mentioned, the boundaries expanding. This expansion was slowing down due to various factors, and primarily the factor was the gravity. Okay, so due to gravity, the slowing down of universe was taking place. Slowing down in the expansion of the universe was taking place. Now, one of the things, or one of the history marking things, happened in 1998, where which could possibly change a lot about astrophysics and the beliefs we have about astrophysics, right? Now, in 1998, it came out so that the measure of, the expansion rate that was into the past, the cosmologists mostly relied on the type 1a supernovae. And if you remember, type 1a supernovae, when we discussed it among type 1a and type 2 supernovae, we discussed that type 1a supernovae was more like a standard candle, which whose light and intensity and the luminosity was taken as a standard reference for all the other supernovae and all the other light emitting criteria that took place in the outer space. Now, these type 1a supernovae, can someone tell me what was the result of a type 1a supernovae? We have already discussed this multiple times.
Neutron star.
Sorry?
Neutron star.
Neutron star is what you're saying?
Yes, ma'am.
Yes. So neutron stars, yes, neutron stars in the form of white dwarfs, most prominently. So yes, these neutron stars or white dwarfs explosions always reached the sort of the same peak luminosity, as we could mark them like standard candles. And these explosions, or these light emits, were taken as the reference for all the other supernovae and all the other light and heat producing events that took place in the outer space. Now, by comparing these, what do you say, the luminosity of these white dwarf explosions or neutron star explosions to their apparent brightness, we could possibly determine their precise distance, right? And by measuring their redshift, hope you remember what redshifts are. By measuring their redshift based on the wavelength that reaches our eyes, we could also know, along with the distance calculation, we could also find their velocity due to the variation in the wavelength falling. Right. Now, the shocking discovery was that the most distant kind of supernovae, that is type 1a supernovae, were slightly more fainter than what they were supposed to be, right? Since they're standard candles, we have their specific luminosity as a reference. And this was a discovery where the supernovae of type 1 kind, type 1a kind, was having a luminosity lesser than what it's supposed to be. Now, if this was happening due to their redshift, then this would be a very shocking discovery, right? So this brought us to a sort of a conclusion wherein that they are further away than they are expected, as in the distance that we have already prior known has been overwritten, or this distance has increased from what we know before this discovery, right? And this could be a proof that the expansion of the universe is accelerating. Now, this is how we know that there is an accelerating universe based on the type 1a supernovae. Hope that's clear. Any questions here?
No, ma'am.
Hope not. All right. Okay, so I'll move into the next one. Now, with this in mind, the gravity has been overcome by something else, because gravity was the major factor that was slowing down the expansion of the universe as believed in the early 1900s, right? So this accelerating part of the universe's expansion could mean that, okay, gravity probably has a different outcome, or gravity has a different way of affecting, right? Now, this acceleration is attributed to dark energy, right? Dark energy is popularly noted by the term lambda, as you can see here. Now, if we were to take a quick look here, we have dark matter that is of 27%, and visible matter is only 5%, and there's dark energy of 68%. So together, 68 and 27, around 95% of the entire universe is of dark area, which consists of dark matter and the subsequent dark energies. So, as this acceleration of the universe is attributed to dark energy, which is lambda, we believe dark energy is sort of a mysterious form of energy that is, inherited to, let's say, space as a fabric. You might know the common or the most famous experiment of the space-time fabric experiment, wherein you try to see how the space-time bends, or the space-time is getting affected by the celestial bodies in the outer space. Now let's consider space as a fabric in itself, and the energy that is that is developed in this sort of fabric due to all the dark matter that is produced is called the dark energy. Now, unlike gravity, uh, like gravity usually, we know that it dilutes as the universe expands, and gravity just sort of merges in and acts accordingly as the universe expands,
Hmm.
right? Unlike this form of gravity, the density of dark energy will remain sort of constant, right? So we can say, comparing gravity and dark energy, we can sort of come up with a conclusion wherein as the space expands, the total amount of dark energy will increase, meaning its repulsive force becomes more dominant, wherein the dark energy stays repulsive and they don't really go along with, as in it doesn't merge easily with the expansion or the accelerating like the gravity would. So dark energy remains a constant without merging up or without being carried over by the expansion or the acceleration of the expansion. Right. So this makes dark energy sort of a dominant force in the modern universe, and with the understanding of its nature, we have come to one of the more bigger challenges in the astrophysics today. So dark energy, a lot about dark energy and dark matter is still looking into, and the features of it or the properties of it are still pretty mysterious to mankind. So how it's able to remain as a constant, why it's not just merging up and sort of having variations according to like how gravity is just merging in, and gravity is just flowing with whatever expansion is being taken place. So that is dark energy. And yeah, so I've just put the same thing as points here. Anyway, so with this note about dark energy versus gravity, as well as the accelerating universe, we are stepping into something called the lambda CDM model. Now, can someone tell me what CDM model means? Like, I believe if someone has looked into this topic for the
Yes.
project or something over the weekend, can you? Yes.
Yes, ma'am. It's the lambda cold dark matter model in which cold, 27% of universe is considered to be made of cold dark matter, and it is called cold and dark because it doesn't interact with any of the ordinary matter.
All right. Yes, absolutely. That's right. Okay. So thank you for that. And so we'll look further into the lambda CDM model, right? So now we sort of combine the topics like the expansion of the universe as well as the CMB, right? Uh, Also, yeah, someone please quickly give me the full form of CMB for those who don't know, or those who don't remember. We discussed all about CMB in the previous session.
Cosmic microwave background.
Sorry, come again.
Cosmic microwave background.
Yes. All right. So, yeah. So we are combining the expansion and cosmic micro background and the dark matter and the dark energy into some sort of current standard model of cosmology, right? So we are trying to put in all those concepts into one model, and that's lambda CDM model. Now, the lambda CDM, or as you have already mentioned, the lambda cold dark matter model, stands for the dark energy, which is, as I've already mentioned, the cosmological constant as we see, because it doesn't really blend into the acceleration part. And the cold typically means that it moves slowly relative to the speed of light. So, as we know, the cold and hot natures in general, hot has a lighter density, so it moves pretty quickly, or it is able to accelerate quickly. Now, cold in nature is more denser than a hot matter, and that will move relatively slower than a hot matter, right? So cold, here in cold dark matter model, we could typically say that cold will move relatively slowly, slower than the speed of light. Now, which is necessary to sort of seed structure the formation. And this model, or the CDM model, is basically very successful because it is sort of simple and uses only six core parameters to accurately predict a lot of standards, right? So, with these six parameters, we are able to predict the sort of observed CMB anisotrops. I've already discussed about the anisotrops in the previous session, the CMB anisotrops. If you want to take a quick look about it, yeah. So we had discussed about how the temperature fluctuations can give you different anisotrops in the CMB map, wherein we discussed about the significance with respect to Kobe, W map, and Planck. How they've plotted all the thermal mapping onto these images. So different anisotrops were found, and due to these anisotrops, different structures were formed over the time. With different technologies we had, right from 1965 to around 2013, we have got different anisotropic structuring with CMB models. Right. Coming back. Yeah. Yeah. So we are able to predict with the CDM model the anisotrops,
The
as
shortest
I've
area
already shown you now. The
the
CMB and
shortest middle.
anisotrops can be predicted, as well as
This
we can
consultant is
predict
40
how the
middle.
distribution of galaxies and clusters are, and also the accelerated expansion. So all of this can be given up by just by looking into the percentages of the dark energy, cold dark matter, and other baryonic matters. And this CDM model gives us the official inventory of the universe. Like, for example, we can get how much of the common celestial bodies, like stars, planets, gas, the Earth, or any celestial body compilation can be understood. And this can also provide various information about the stuffs that make up the stars, planets, what the components or the composition of the various celestial bodies are. And also the cold dark matter, which is around 26.8%, as mentioned here. And the cold dark matter, apart from the dark matter, which is that sums out to 95%, other than the baryonic matter, out of that, the cold dark matter can also be specifically understood due to the gravity that it acquires. Right. So um, the repulsive force that is driving the acceleration is basically the dark energy, as I've already mentioned. Now the model will tell us. Sorry. All right. So the model that has already told us that around 95% of the universe is composed of components that we don't know actually, or rather we could call it the dark matter. Uh, we can sort of understand the reality of modern science through the CDM model, which will give us all this information plus how the effect of dark energy constant and gravity go hand in hand, right? So if I were to give you a clearer idea, yeah. So this is the expansion model that is proposed as of now, wherein we check the dark matter and how it has widened out into a fixed boundary, but that fixed boundary is expanding, as in it's a finite boundary that is being expanded, right? And as I've already mentioned, we had in the early 1900s, we thought it was very gradually increasing, as in the increase was very gradual, because as you can see here, this part is very narrower, and this narrow part was what we could study back then. And later we saw that due to the influence of dark energy over the gravity, we could understand that this gravity was just merging and giving us a sort of a sly picture, or it was just manipulating our brains to thinking that it was very gradual. But apparently it was just expanding very it was accelerating in a very quicker scale, but the gravity was just going along with the flow, so we couldn't really understand the difference. Now only when we could research and identify there was a dark energy that was staying constant, only then we could understand how big of an acceleration or how fast of an acceleration was taking place. So that is the whole idea of the CDM model. Now, coming to the fate of the universe. Now, if you remember, this was one of the topics covered in the project. So, to give you a sort of an idea about the dark energy and its dominance and how it can determine the fate of the universe, I'll be discussing it in this slide. So, our understanding of the dark energy and its dominance sort of fundamentally um, dictates or determines the ultimate fate of the cosmos, right? So, since dark energy's density remains almost a constant and not really just being molded according to how the expansion happens, its repulsive forces will become more stronger relative to gravity over time, and this leads us to the scenario known as the big freeze. Now, the big freeze, or it's also called the heat death. Can someone come up and tell me what big freeze or the heat death is? If you don't know,
Um,
please Google it up as soon as possible
ma'am,
and tell
I
me.
actually know about from like this, the Stephen Hawking's book, the from a brief history of time. So I can tell
Okay.
as much as I know about that.
Yes, please, please,
Uh,
please.
in this prediction, as I mean, the dark matter remains constant. So the start, I mean, and the ordinary matter is also constant. So as we move further in time, uh, there will come a time when I mean the matter will be exhausted and the stars will die. The stars will cool
Okay.
down, and I mean the last of the stars will
Mm-hmm.
eventually, after millions, hundreds of millions of years, will run out of fuel. That will leave
Okay.
the only oldest generation of stars, which will be the white dwarf, neutron stars, and the black holes.
All
Then
right.
after that, the white holes will, after more millions of years ago, after they will also meet their eventual death, which is becoming a black dwarf and eventually become cold matter. And then there remains neutron star and black hole. Then after some millions of years come the turn of a neutron star, they will eventually evaporate. And as the longest that will survive will be the black hole for even more of time, and that is called the dark age. It's in Hawking's book.
Mm,
So and after that, due to the Hawking's radiation, the last of the black holes will evaporate, leaving
mm,
only cold matter, which will be the heavy metals that are like forms during stars and life cycle end, like iron or other heavy metals. So those will remain, and I mean they will not be much heat. So that it's called big freeze because that will be thermal equilibrium with very less temperature. And I know I'm not very correct because I only remember which.
No problem. Whatever you've told about the big freeze or the heat death or the dark age is absolutely right. Now, one question I have, Praful, is have you thought about what about the new stars that are being formed during this period?
Yes, actually, the thing is, the new stars are forming, but as I said, it will take a long time because
Hmm.
eventually, it's true that the new stars are forming, but also some like matter is getting lost due to during that formation, which leads to the formation of heavier metals as we see in the
Hmm.
universe.
Okay.
While stars relies on lighter fuel, like hydrogen, helium, for their energy. And eventually,
Hmm.
there will come a time when all the, I mean, since we assume the ordinary matter to be constant, there will come a time when all the matter will be transformed into that kind of heavy metals, which will be cold and not be able to perform fusion, which will actually fuel any star.
All right. Okay. That's
That's my
partially
assumption.
right.
Actually, I
Yeah.
haven't studied it. That's only my, I mean, assumption. So I may be wrong. So please
No
correct me.
problem. No problem. But the core idea of what you've discussed is absolutely right. All right, so let's look further into this. So, as you have mentioned about the big freeze and heat death, wherein the fuel gets exhausted and it further creates havoc. Yeah, anyway, we'll look into it. So, what happens here is, as Praful has mentioned, the acceleration will keep increasing, pushing all the galaxies that are not gravitationally bound to our local group. Okay, so this binding is keeping all our galaxies in place, okay, within the boundary. Now, all these will be accelerated and pushed over the cosmic horizon. Now, cosmic horizon is basically just the cosmic boundary, right? So it'll be pushed across the boundary and they will be moving away from us so fast that their light will eventually be stretched beyond detection. That it may look infinite to us, but it is just stretched across, that it is not visible, or it is not falling into our eyes or into any sort of equipment that we use. All right, so they will be moving at a very fast rate. And in the far future, as this faster rate keeps increasing, in the far future, the stars will exhaust their fuel and eventually their stellar remnants will become colder and they will cool down, and the black holes will also eventually evaporate. And that evaporation is caused due to the Hawking radiation. Praful had mentioned that term as well. Good. So Hawking radiation is nothing but it's sort of like a leakage. Okay, so the black hole is just leaking and it's having its remnants just just going oozing out of control. Right. So Hawking radiation is basically the theoretical thermal energy emitted by a black hole, and this thermal energy is just oozing out of it without uncontrollably. And this is happening due to quantum effects, and this quantum effects typically happen near the event horizon. So due to this quantum effects happening at the event horizon, there are holes, or there are some sort of um, you know uh, the stretching just increases spaces in between and just causes some sort of loopholes in between for the thermal energy to escape. Right. Now, this Hawking radiation typically occurs when some sort of spontaneous virtual particle or anti-particle pair are formed, and these pairs are typically formed near the boundaries, and so there is like particle anti-particle pairing that will cause this spontaneous events wherein it will just accelerate the thermal energy to just pushes the thermal energy to just outside the boundary or through these loopholes that is formed. Now, what happens when there is a pair of particle and antiparticle? One particle will fall in. Let's say this particle carries some sort of negative energy and it will just fall in, and this will reduce the black hole's mass as the particle falls in, and the other one just escapes into the space as radiation. So in the pairs, there is at the boundary, the mass part will fall back into the black hole, and whatever is remaining antiparticle part will just escape through the loophole as radiation. Now, this process will typically mean that the black holes are not truly black, right? So they'll slowly start losing mass and radiation over time, and they will have some sort of evaporation happening because the thermal energy is escaping as well. And all these will happen over a very vast cosmic time scale. And this concept of the time scale increasing and eventually it losing all the thermal energy, all this concept is basically linking the whole quantum mechanics and general relativity. I'm sure you're familiar with general relativity theorems and quantum mechanics. So all these are a major part which links both quantum mechanics and the relativity theorems, right? So after the Hawking radiation happening, the universe will become very dilute. Like it'll start getting increasingly diluted because it's losing all the thermal energy, and plus the mass is also, some are just evaporating, some are just staying there because of the remaining thermal energy it has. So the universe will become increasingly dilute. It'll be cold and dark, and it'll just keep expanding, and this will be dominated by whatever comes in the opposite part of dark, photons, right? So this will be dominated by photons and neutrinos, etc., because the molecules are just splitting up, and the particles are just evaporated, sort of. Some part is evaporated, some are still trapped, some are just escaping as radiations, etc. Now whatever is remaining is being dominated in that presence by the photons and neutrinos that is present, and it will be a universe of let's say a thermodynamic equilibrium. And this thermodynamic equilibrium is called the heat death, and that is imagined to be where the this equilibrium coming into place. When this equilibrium happens, that is where the fate of the universe is decided. Now there is a heat death, and there is no longer, the universe will be able to support various celestial bodies, and it won't be able to support the stability of everything that is in it together. Now the lambda CDM model will offer some sort of a complete framework, but this framework that we get through lambda CDM model has two massive holes. Okay, two loopholes that we are not able to fill up with. One is dark matter and dark energy, which a lot of controversies, lot of discussions, theorems, researches are still going on. And this is where the future of cosmology basically lies. And if y'all can include a lot of your, I mean, whoever is taking the dark energy or dark matter topics, please make sure that you include something about the fate of the universe and how you look into it and what sources you get. That will be an added advantage when you're present, so everyone can ask questions and get to have a better understanding about it, right? So if I were to discuss the CDM parameters here, we have mass density, that is omega m, and dark energy density, that is omega lambda. Now we have plotting of the omega dark energy and omega matter, and if we were to connect a line from 1 to 1 of both omega dark energy and omega matter, then we could see that the clusters are more or less inclined towards the dark energy. The supernova is happening sort of perpendicular to the one-on-one, and CMB is happening more inclined towards the lambda matter, the mass of the matter. So it's a very simple graph that is just showing you the mass density and the dark energy density that is in the CDM parameters. So that is it. Our today's session is just this much, and I will quickly show you. Once again, I'll just revise the our last session's project that I put forth in front of all of you, so that we can, those of you all had missed can have a quick look through it. Just share. I'm just sharing it directly. Yeah, is it visible? Okay, hope that's visible. Okay, so these are the four topics that we have considered for our project, and we have this project termed as astrophysical synthesis because you will be synthesizing from the four topics. It is research and presentation oriented. Now, the goal, you will have to demonstrate an advanced understanding of the courses that we have already covered, that is, including stellar evolution, compact objects, galaxies, and cosmologies. And you have to at least draw three of these four domains. And yeah, so you must make sure that you include some quantitative context, right? Diagrams, equations, or some parameter values or data plots, whatever you feel is relevant to the topic. And we will be evaluating based on these three criteria majorly, and about how much you're able to understand whatever you've presented. So I would highly suggest you that whatever you're putting on your PPT, make sure you know about what you're putting on your PPT. Whatever questions are raised or whatever discussions we come into, make sure that you're able to go around the topic. And if there are any confusions with it, please have a note or whatever you would like to refer for your quick access. And yeah, now I had just given you a quick criteria on the relevance of each topic and why it is important to have each of these topic connected into your presentation, wherein we discussed how stellar evolution ultimately leads to some sort of death of that star from birth to the death, and then death eventually gives rise to supernovas, which gives rise to compact objects, and those compact objects can give rise to galaxies and various other celestial bodies, and it can ultimately lead into cosmology as well. So it is all interconnected. You can't really take it as separate topics. You would be anyway touching a lot of topics when you discuss about these. uh, yeah, so this is one major challenge you may face, and that is about moving beyond the defining terms. So please make sure that whatever we have already defined in our previous sessions, try not to put exactly like that. So try to get more advanced information, and it's highly suggested to go through some article researches and some documents if you can find any. If the I think the best options you can have is than um, more than Google materials. You could be getting more advanced things from any nearest libraries or so. For me personally, I think the best informations I've got over not just for these sessions but over the whole astrophysics, the understanding and learning of the astrophysics, the best were some library materials. So if you could do that, that'll be great, as your time permits. And please make sure that you put all the relevant references that you have used in one of your slides. And yes, that's all you will have to take care of. And your topics, five topics were given to you. One was Type 1a supernovae and the cosmic tools. Then we have dark matter from halo to horizon. We have Aegean feedback and galactic coevolution, the epoch of reionization, and the final eons of the universe. Now, final eons of the universe is where I've covered a basic part of it in today's session. So you can check in the advanced manner. You can check in detail about the Hawkins radiation, the big freeze, the heat death, all of that in detail, and try to come up with facts that interests you the most. And all of these other topics like the supernovae, dark matter, agent feedback, all of that has been already covered in previous sessions. If you have any doubts, please make sure you go back to the recordings and check, or you could probably be getting more, what do you say, easy explanations from any other sources as well. So check out whatever helps you. And yeah, so I've given you each topic, what it covers, the synthesis that is required from that particular topic, wherein each topic will be covering at least three of the four domains that that we have discussed in previous sessions, and what you have to be focusing on primarily. Now, this is just a primary topic that I'm giving you. But please make sure that you take it to a different level, you take it to an advanced note, and some advanced element suggestions I've given you as well. You can refer these, or you can go for anything that is associated to this or not associated to it. Make sure you have some advanced topics covered within the, within the title I've given you. So similarly, I've given you for 1, 2, 3, 4, and 5. Okay, so the final eons of the universe, we have discussed about the ultimate fate of all matter based on the CDM model. So I've just introduced what the CDM model is to you, and how the ultimate fate or the acceleration has led to, will be leading to in the future. That has also been discussed. Now you can check into the advanced elements, and you can come up with your presentation accordingly. So that is all. This is your yeah. So this is your topics, and this is your presentation. And your presentation, please note that your presentation is on 17th Monday and 18th Tuesday. So we'll be having 2 consecutive days of session, wherein each of you will be getting a maximum of 8 to 10 minutes. Please try to keep your presentation for 8 minutes, so that we can utilize another 2 minutes for discussions and reviews. Hope that's clear to everyone. Guys.
Yes.
All right. And if at any point you have any confusions, please feel free to reach out to me. WhatsApp would be the best. But if we are beyond the time of the assignment submissions or any sort of, uh, please do not bother texting me asking for extra time and all of that, unless you have a very valid reason. I would completely understand. I have also given some extra time based on your reason. I completely understand that. But if you are texting me saying you wouldn't be able to, find time for this next week, or you don't have enough time to prepare all of that, I'm sorry. I really appreciate that. I'm sorry, but that is why I've given like a solid 10 days time. Presentation you can come up with in maybe 2 3 days of research. So please make sure that you come up with some solid content, and let's see how it goes. Yeah. So from the next session, we'll be starting our observational techniques. And before that, maybe I am planning to have one session this week wherein we discuss about all the previous assignments that you have submitted, and we have a discussion on how you can make it better, or how individually we can look into each of your projects. Yes. So I'll be picking few assignments, and we'll be discussing on that. Hope that's clear. I hope that's clear. All right. So that's it. We have come to the end of our session. If you don't have any questions, we can call it a day. If you have any questions, please feel free to shoot. Yes, Nimit, Likit,
No.
what do you all think? Any questions? Praful?
No, ma'am, I don't have any question in particular. Actually, I
Okay,
should.
so normally, yes, sorry. What were you saying?
I mean, actually, ma'am, I have picked the topic that was the final
Mhm.
eons of the universe. So, like,
Okay.
should we add the like the I mean the ways in which universe can end, according to the lambda CDM model, or like other prediction like false vacuum decay or other.
That is an advancement you can choose. That is for sure. You can come up with other models as well. Uh, I'm sorry, my laptop is running out. Okay.
Okay.
If the class gets cut off in between, please understand. I'm not in a position to get my charger right now. But yeah, that is definitely an advancement you can come up with. You can definitely go for other models as well. That will be an added advantage.
Okay, ma'am.
Yeah. Anyone else? Any questions? Saumali, Preyashi?
No, ma'am, I have chosen AGN feedback and galactic co-evolution. So I'm still searching and researching actually. So if there are any
Okay, okay.
question, there is any question, I will definitely WhatsApp you.
Yeah, sure, sure. Please, please do. And that's a great topic. And all those topics are really, it has a huge area to research on. It has huge, what do you say? It has vast information. It's a
Yes,
big
ma'am.
opportunity to look through. So, yes, feel free to choose any topics and feel free to reach out if you require any more information or any support. Sure.
Yes, ma'am.
Yeah.
Thank you, ma'am.
Okay. Thank you. So, thank you, everyone. If you don't have any other questions, we can call it a day. All right. So, thank you so much. Bye bye.
Thank you, ma'am.
Thank you. Bye. Suman, Brishake Tubera, Kali Prasanna, do we have any questions? All right. I guess we don't have any questions. I'm going to remove you all from the call.
ओ दादा क्या बोल रहे हैं कौन सा जगह पे जाना है बता देगा एंट्री करोगे
अरे भाई बात कर जल्दी ना भाई।
हाँ बोलिए
क्या किसको दे फोन है, तो मैं बोल रहा हूँ ना एड्रेस।
हाँ ये एसीसी गेट है मेन गेट है
एसी गेट का है ना, तो
हाँ
डेड एंड आ जा, डेड एंड लेफ्ट लो और डेड एंड लेफ्ट लेके लेफ्ट ले लो। आपको बड़ा हैंगर दिखेगा, उसके अंदर लगना है।
एक बार रिपीट करिए गाड़ी साउंड हो रहा है ना सुनाई नहीं दिया
एक डेड एंड एकदम वैसा डेड एंड आके लेफ्ट लो,
अच्छा
तो आपको हैंगर दिखेगा। उधर आके एक हार्ट देखो, हार्ट डाले हैं तो आपको दिख जाएगा। डेड एंड लेफ्ट लो।
ओके ठीक है सर मैं अभी लेकर आके आता हूँ
बंदे का नंबर दे रहा हूँ मैं,
हाँ
ये एंट्री करा देगा, वो कॉल करेगा देखो तुमको।
ठीक है করবে নাকি? না গাড়ি নম্বর মোবাইল নম্বরটা হ্যাঁ দিয়ে দাও। ছবি তুলে নিতে হ্যালো हाँ बात होने किससे लगे तो जो हरियाणा नाम से चले काम वाला लोग नाम से बात कर रही है कंपनी नाम से कौन कंपनी में जाए खाली तो दो जाते हैं हाँ मतलब कि कौन जगह जाएगी तो मुझे पूछेगा मैं हमारी काम मालूम ना কিছু বলছো हाँ ठीक